So this is lecture 14 of differential equations. And let me recall, we started with Laplace transforms last time. So it's a linear transformation. L of f is a function whose value at s is integral 0 to infinity e to the minus st ft dt, and we saw what the meaning of this improper integral is, and we actually computed. We had the following table: f versus lf, and the functions were f is 1, lf is 1 over s. Again, I denote the variable by t when it is f, and when it is lf, the variable will be s. So Laplace transform of t to the n is factorial n over s to the n plus 1. E to the at, Laplace transform is 1 over s minus a. Sine at is Laplace transform is a over a square, s square plus a square. And cos at, which is what I asked you to check at home, and I am assuming that you have proved this. And then the rules. First of all, Laplace transform is a linear transformation. So L of f plus g is Lf plus Lg. L of lambda f is lambda times Lf. And then I had mentioned two rules which I will prove. Laplace transform of the derivative at s is s times Laplace transform of f at s minus f of 0. And the third rule was Laplace transform of the integral f tau d tau at s is 1 over s times Laplace transform of f at s. So let's see the proofs of these two results. So proofs of 2 and 3. So let me quickly prove this. So if I look at Laplace transform of f prime, this is integral 0 to infinity e to the minus st f prime t dt, which is interpreted as limit as m tends to infinity, integral 0 to m e to the minus st f prime t dt. And now I'm going to apply integration by parts by integrating f prime first. So integral of f prime is f times the other function 0 to m minus the integral of the integrated function, which is ft, times the derivative of the other, which is minus s times e to the minus st dt. So this is going to give you lim as m tends to infinity. Value at m is going to be fm e to the minus sm minus the value at 0 will be f of 0 minus this minus and that minus gives you plus s times 0 to m ft e to the minus st dt. But if you look at this, then this limit, the first limit is 0 because e to the minus sm tends to 0. You get minus f0 plus s, and then you get exactly what the definition of Laplace transform is for Laplace transform of f. So this becomes minus f0 plus s times Lf. So that's the proof of 2. This proves formula 2. And now if I want to do Laplace transform of, so let's call that 2. And to prove Laplace transform of the integral, let's write down the integral of ft dt. Let me write integral of f as function g. So this is going to be integral 0 to infinity gt e to the minus st dt, so which is equal to lim m tends to infinity 0 to m gt e to the minus st dt. And now I'm going to integrate e to the st first. So I'm doing integration by parts. So integral of that is e to the minus st by minus s times g evaluated between 0 to m minus integral 0 to m integrated thing, which is e to the minus st by minus s times the derivative of g will be f, because g was integral of f. So this is going to be limit as m tends to infinity e to the minus sm by minus s times g m minus, when you evaluate at 0, you are going to get e to the 0 g of 0 by minus s, and then you are going to get plus 1 over s integral 0 to m e to the minus st ft dt. Now note that g of 0 is 0, therefore, and this limit tends to 0, so you will get 0 minus 0 plus lim as m tends to infinity 1 over s integral 0 to m e to the minus st ft dt. But that's exactly 1 over s comes out, and that's exactly the Laplace transform of f. So the Laplace transform of integral of f is 1 over s times Laplace transform of f. So this proves 3. So both formulae were direct consequences of integration by parts, and then we learned last time, I think I did one example showing how to use the formula for Laplace transform of the integral to read off the inverse transform. So let me do a couple of problems to recall that. So problem, let's say LF of s is 1 over s square plus s, find f. So you observe that LF has 1 over s in the denominator. It's 1 over s times s plus 1. And you can recognize, if you ignore this 1 over s, then we can recognize the inverse transform of 1 over s plus 1. This is e to the minus t. So therefore, the inverse transform of 1 over s times s plus 1 will be the integral 0 to t e to the minus t dt. I should have actually used a variable tau here, but it doesn't matter. E to the minus t integral is minus e to the minus t, that's between 0 to t. So it's going to be minus e to the minus t minus e to the 0, which is 1. So the answer is 1 minus e to the minus t. I could have done this also by using partial fractions, but this gives you this shows you how to use this formula. So if you have a factor, for example, if you have a, and let's do one more problem. Find the function f where LF of s is 1 over s squared times s plus 1. So you have two 1 over s's here. So we know, we just showed that L inverse of 1 over s times s plus 1 is 1 minus e to the minus t. Therefore, by the integral formula, by the formula for the integral, we know that L inverse of 1 over s times s times s plus 1 would be the integral of this function 1 minus e to the minus t. So this will be t plus e to the minus t. That's the integral of this quantity between 0 to t. So this gives you t plus e to the minus t minus the value at 0 will be that. So this will be t minus 1 plus e to the minus t. So this is the way you will use the formula for the inverse. Whenever you see a factor of 1 over s, then you integrate the inverse transform of the remaining term. Now we shall see how to solve differential equations or initial value problem. So now we shall see how to solve an IVP using Laplace transforms. So before we begin, let me recall two things that we'll need. We'll need the formula for Laplace transform of f prime. That is at s, it's s times lf minus f0. And therefore, Laplace transform of f double prime will be Laplace transform of f prime's prime. So that's going to be s times Laplace transform of f prime minus f prime 0. And then Laplace transform of f prime is s lf minus f0. So therefore, Laplace transform of the double derivative of f is s square lf minus sf0 minus f prime 0. This formula you want to remember. So if you take higher derivatives, you will get higher powers of s multiplying lf. So when you had the first derivative, it is s times lf minus f0. And for second derivative, you get s square times lf minus s times f0 minus f prime 0. So now let's do one problem on solving. So let me formulate it this way. Solve the IVP y double prime plus 3y prime plus 2y equal to 0. The initial condition is y at 0 equal to 1, y prime 0 equal to 0, using the method of Laplace transforms. So this is not difficult. What you do in this case is we take L of both sides. So we think of this as vectors and you are applying linear transformation to these vectors. So take L of both sides. So that will say L of y double prime plus 3y prime plus 2y equal to L of 0. And L of 0 is always 0, that you can easily check. And now L being linear, the left hand side is Ly double prime plus 3Ly prime plus 2Ly. I can write L of sum of two functions as sum of L of two functions. And L of lambda f is lambda times Lf. That's 0. Now I'm going to use the formula that we just saw. L of y double prime is s square Ly minus sy0 minus y prime 0. This is my first term. Plus 3 times Ly is Ly prime is Ly minus y0 plus 2Ly equal to 0. So now you are given the initial conditions. Y of 0 is 1, y prime 0 is 0. So this gives you s square Ly minus s, because y0 is 1, y prime 0 is 0, plus 3s Ly minus y0 is 1, plus 2ly equal to 0. Now let's collect the terms with ly. So you get s square, I pull out ly, so you get s square plus 3s plus 2 ly minus s minus 3 equal to 0. So this is what I mean by getting an algebraic equation for ly. This equation is very easy to solve. So this will say ly equal to, if you take s and 3 on the other side and you divide by s square plus 3s plus 2, you get a formula for ly. And now y is going to be the inverse transform of this. So this will give you the solution. So our solution y is L inverse of, now you see why it is important to be able to find out the inverse transform of a given function. The denominator here factors, so we will use partial fractions to write the expression. This will be s plus 1 times s plus 2, and so we use partial fractions so to write down the fraction of polynomials that you have. This I will write as a over s plus 1 plus b over s plus 2. So you get s plus 3 equal to a times s plus 2 plus b times s plus 1. That gives me coefficient of s, which is 1, must be coefficient of s is a plus b on the right side, and coefficient of s to the 0 is 3, which is 2a plus b. So if you want to solve this, I subtract the equation 2 from 1, so I get minus 2 is equal to minus a. So a will be 2 and b therefore is minus 1, isn't it? Because a plus b should be 1. So therefore our solution y, which is L inverse of s plus 3 over s plus 1 times s plus 2, is L inverse of 2 by s plus 1 minus 1 over s plus 2. As L inverse being linear, you can split it like this. 2 you can take outside because L inverse is linear. And now you go back to the tables and you will see the inverse transform of 1 over s plus 1 is e to the minus t. And the inverse transform of 1 over s plus 2 is e to the minus 2t. So that's our solution. So this is the procedure of solving a initial value problem using the method of Laplace transforms. You start by taking L of both sides. You will use the formula for the derivative and the double derivative of a Laplace transform. That will give you an algebraic equation or a algebraic expression for L of y, and then you read from that y. From L of y you read y by using the method of finding the inverse transform. So let's do one more. So solve the following IVP. Using the method of Laplace transforms. So let's take something like y double prime minus 2y prime plus 3y minus 3y equal to 0, y of 0 equal to 1, y prime 0 equal to 7. Good. So we'll start by take L of both sides. In other words, the proper way of saying this is apply L to both vectors on the left side and on the right side. So L of y double prime minus 2y prime minus 3y equal to L of 0, which is 0. The left side is L of y double prime minus 2ly prime minus 3ly. That should be 0. Now comes the place where you use the formula for the derivatives. Laplace transform of the derivatives. Laplace transform of Ly double prime is s square Ly minus s y0 minus y prime 0 minus 2 times Ly prime is s Ly minus y0 minus 3Ly equal to 0. So I collect the terms in Ly. I will get s square minus 2s minus 3 Ly minus whatever is left sy0 minus y prime 0 from the first bracket, and here you will get plus 2y0. That should be 0. Now you are given y0 and y prime 0, so I substitute those values. y0 is 1, y prime 0 is 7, and y0 is 1. So this gives you s square minus 2s minus 3ly equal to s. I move these s. On the left side you get minus 5. When you move it to the right you get plus 5 on the right side. So Ly is going to be s plus 5 over s square minus 2s minus 3. You can factor the denominator. It is s minus 3 times s plus 1. And so now you have to find out the inverse transform. So therefore y will be L inverse of s plus 5 over s minus 3 times s plus 1. So again use partial fractions. Again we use partial fractions of this polynomial quotient. So I want to write s plus 5 over s minus 3 times s plus 1 as a over s minus 3 plus b over s plus 1. So that tells me that s plus 5 must be identically a times s plus 1 plus b times s minus 3. So I now equate coefficients of s to the 1. On the left side it's 1, on the right side it is a plus b. And the coefficient of s to the 0 on the left side is 5, on the right side is a minus 3b. So if I subtract, I will kill a and I will get b minus 3b is 4b. So that gives you b equal to minus 1, so a must be 2, because a plus b is 1. So therefore y, which is L inverse of s plus 5 over s minus 3 times s plus 1, that's L inverse of 2 by s minus 3 minus b is minus 1, so it's 1 over s plus 1. By linearity of L inverse, this is 2 by L inverse of 2 by s minus 3 minus L inverse of 1 over s plus 1. 2 will come out because of linearity, and then the answer, where you can read off the inverse transforms of this from the table. This is going to be e to the 3t, the other thing is e to the minus t. So that's your solution. So now to do more complicated problems, we will need to have more strength in reading of the inverse transforms. So we will now learn 2 more tricks to find out the inverse transforms. So now we add to our arsenal, to our list of rules or list of formulae, 2 more useful formulae called shift formulae, shift formula 1 and shift formula 2 for the next lecture. So let me begin with shift formula 1. So what it says, again I draw this picture of this box L. If you take a function f and you multiply it by e to the at and pass it through the box, then what comes out is LF not at s but at s minus a. So multiplying the function that you input by an exponential function, what the box converts it into finding LF not at s but a translation of s by a. So in other words, the exponentiation, multiplying by an exponential function, is converted into a shift. That's why it is called shift formula. It is not s but s is shifted by a. So in other words, the result is Laplace transform of e to the at times f t at s is Laplace transform of f at s minus a. And this is easy to prove, and I will tell you now, this formula will give us a very good tool for finding many more complicated inverse transforms. I mean complicated inverse transforms of complicated functions. So the proof of this is not hard. Let's try to calculate this at s. This is as before, integral 0 to infinity e to the minus st e to the at ft dt. But as you can see that this is simply e to the minus s minus at ft dt, and this is nothing but Laplace transform of f but at s minus a. That's the definition of, what is the definition of Laplace transform of f at a given point? S star. It is e to the minus s star t ft dt. So the proof is very easy. So how do we apply this? So let's see. So we shall now see how this formula can be used to find the inverse transforms. So example, find f given that LF at s is 6 over s minus 2 to the 4. So you see, the way to think of this is, since L of e to the atf is L of f at s minus a, that says that L inverse of L of, so that means if you can recognize LF, then if you want to find out L inverse of f of s minus a, it is e to the at times f. So now note that you should be able to figure out L inverse of 6 by s to the 4, and then you will see that this is a shift by 2. So your a is going to be 2. But first of all, let's figure out this. So what is a function whose Laplace transform gives you 1 over s to the 4? It's t cube. L of t cube is factorial 3 over s to the 4, which is actually 6 by s to the 4. So L inverse of 6 by s to the 4 is t cube. Therefore, by the shift formula, L inverse of 6 over s minus 2 to the 4, this is the Laplace transform of t cube evaluated at not at s but at s minus 2. So it must come from the function which is t cube multiplied by e to the 2t. So if you take the Laplace transform of e to the 2t times t cube, you get the Laplace transform of t cube not at s but at s minus 2, which is exactly what we have. So this is our answer. So this is the way you will apply the shift formula to find the inverse transforms. So let's do another one. So now we use this now shift formula 1 and the trick of completing squares can be used together. So maybe before writing this, I will just mention this as a remark. So shift formula 1 and the algebraic trick which you have used in calculus a lot of completing squares, and I'll show you what I mean by this. So shift formula 1 and the algebraic trick of completing squares will help us in computing inverse transforms of many more functions. So let's see how that is done. So another problem. Let's take LF of s to be 2s plus 1 over, maybe I'll write this as s square plus 2s plus 5. How about that? Or maybe I'll make it nicer. So I want, no, that's fine, 2s plus 5. So now we don't know what this function is, and the denominator doesn't factor. So note that denominator doesn't factor. This is where you will use shift formula 2. So if the denominator factors, then you will use the trick of partial fractions. If it doesn't factor, we'll use the trick of completing squares. So we proceed as follows. So now we are looking at f, which is L inverse of, so partial fractions cannot be done here because the denominator is irreducible quadratic. So I write the denominator by completing squares. So I will write s square plus 2s. To complete square, I will have to have a 1. That will be a square of s plus 1. Then I will have to have 4. And now you can think of this as L inverse of 2s plus 1 over s plus 1 square plus 4. 4 will be thought of as 2 square. Now you should recall that Laplace transform of cos AT is s over a square plus s square. So this expression should tell you that if you had s over s, not this expression 1s plus 1 square tells you that if you had s plus 1 on the top, so let me rewrite this by writing 2 times s plus 1 over s plus 1 square plus 2 square. This s plus 1 over s plus 1 square plus 2 square is just the Laplace transform of cos 2t shifted by minus 1. So you want to write the expression like this because the inverse transform of this you can find. But this is 2s plus 2, so I have to subtract 1. So these are the algebraic tricks, and so I will now split this in two terms. 2 times s plus 1 over s plus 1 square plus 2 square minus L inverse of 1 over s plus 1 square plus 2 square. This 2 you can pull out, and so you get L inverse of s plus 1 over s plus 1 square plus 2 square, so which is going to be, this is exactly the Laplace transform. Let me see, my pen has stopped working, so I'll charge it in 13 seconds. Hang in there just for a second. Okay, I think this should work now. Yeah. And then for the second one, you see the other formula that you will need is Laplace transform of sine 80. L of sine 80 is A over s square plus a square. So a is 2 here because you have 2 squares, so you have to have a 2 on the top. So you will write this as L inverse of 2 divided by s plus 1 square plus 2 square, but we don't have a 2 on the top, so I divide by 2. So then this will be 2 times, this is the Laplace transform of cosine of 2t shifted by minus 1. So it's going to be e to the minus t cos 2t. And this is the same thing as Laplace transform of sine 2t shifted by minus 1. So its inverse transform is going to be e to the minus t sine 2t. And that's going to be your solution. Well, not a solution here. We are not solving a initial value problem. This is going to be the inverse transform. So this is a prototype of a problem where you see how you can use shift formula 1 combined with the trick of completing squares to find the inverse transforms. And this is what you will use typically when your LF is having a denominator which is irreducible quadratic. So let's do one more. Find, so another problem. Find f given that LF of s is, let's do this, s over s square plus 6s plus 10. So again, the denominator is irreducible quadratic. That means you have to use, first you start by completing squares and then you use the shift formula 1. So let's write down f as L inverse of s over s square plus 10, 6x plus 10, which you will write as, by completing square you have to have 9, isn't it? That will be s plus 3 square will give you 6x in the middle. So I will split 10 as 9 plus 1 and rewrite this as L inverse of s over s plus 3 square plus 1 square. Now you know what to do. I would like to have s plus 3 on the top so that this will remind me of s over s square plus 3 plus 1 square, which is the Laplace transform of cos t. So let's do that. So I will write s plus 3 on the top. I don't have plus 3, so I will have to subtract. So split this in 2 terms. Plus 3 minus 3. And which is going to be L inverse of s plus 3 over s plus 3 square plus 1 square minus 3 L inverse of 3 over s plus 3 square plus 1 square. And the first one is going to be, the shift is by minus 3. Your a is 1, so it is e to the minus 3t cos t. Now for the second one, this 3 will come out and you will write this as 1 over s plus 3 square plus 1 square. So you will get 3 will come out, and then you will see that that's just the Laplace transform of sine of t shifted by minus 3. So its inverse transform is e to the minus 3t sine t. one more. So find f given that LF of s is 2s minus 3 over s square plus 2s plus 10. So again, denominator doesn't factor, so you always pay attention to the denominator. If it factors, you use partial fractions. If it is not factorizable, if it's a irreducible quadratic, then you use completing squares and shift formula 1. So this is going to give you, therefore f will be L inverse 2s minus 3 s square plus 2s plus 10, which is, complete the squares. To get the 2s in the middle, I have to have 1. What's left is 9, so you write this as L inverse 2s minus 3 divided by s plus 1 square plus 3 square, and then do whatever it takes. So you want to have shift by 1, so you will have to get the shift on the top s by 1. So I want to write this s as s plus 1. So I will have 2s plus 2, I have minus 3, so I have to subtract 5. Then I know I will split first of all this into two terms. 2 can be written outside. You get s plus 1 over s plus 1 square plus 3 square minus 5 times L inverse of 1 over s plus 1 square plus 3 square. This is just going to be the Laplace transform of cos t, but shifted by minus 1. So its inverse transform is e to the minus t cos 3t. A is 3 here. Now here again it's sine, but sine, Laplace transform of sine 3t is 3 divided by s square plus 3 square. So I got to have 3 on the top. So I put 3 on the top, but then you divide by 3. And then you recognize this as a Laplace transform of sine t, but shifted at minus 1. So the answer to that will be minus 5 by 3 e to the minus t sine 3t, not 2, 3. So that's how you compute the Laplace inverse transform. Maybe it's a good time to do one more differential equation and then I will stop, because then I want to do shift formula 2, not in the same stretch. So this lecture will be a bit shorter. Let me do one more problem. And let's see. Let's do one problem on solving a differential equation or an initial value problem. Yeah, let's do one last problem. So let's try solve the IVP y double prime plus 2y prime plus 5y equal to 0 with y of 0 equal to 2 and y prime 0 equal to 1 equal to minus 1 using Laplace transforms. So we'll always start by taking L of both sides. That means again apply the linear transformation L to these vectors on both sides. These vectors are functions in the space of continuous functions. L of 0 is 0, and the left hand side is Ly double prime plus 2 Ly prime plus 5 Ly That should be 0. Then by using the formula for the derivative, this is s square ly minus sy0 minus y prime 0 plus 2 times ly is ly minus y0 plus 5 ly equal to 0. So I collect the terms in ly, pull ly outside, so I'll be left with s square plus 2s plus 5 ly. Then I have a minus sy0 minus y prime 0, these two terms, and then this term will be plus 2y0, and that should be 0. So I get s square plus 2s plus 5 ly minus, and now I use the initial conditions. Y of 0 is 2, y prime 0 is minus 1, so this becomes plus 1, and y of 0 is 2, that should be 0. So that says s square plus 2s plus 5 ly is equal to, I move these things on the other side, is 2s minus 3. So ly is going to be 2s minus 3 over s square plus 2s plus 5. And so now we have a situation where you have to find the inverse transform, and the expression whose inverse transform we are seeking, its denominator doesn't factor. So you have to use shift formula 1 here. So you just complete squares, that's the first step. So these are algebraic tricks. So you will write this as s plus 1 square, which will give you s square plus 2s plus 1. What's left is 4, which you will think of as 2 square. And then I want s plus 1 on the top also. So I'll write 2 times s plus 1. That will give me 2s plus 2. I want minus 3, so I subtract 5. And then I write this as s plus 1 square plus 2 square. And then split it into 2 terms. So it is 2 times L inverse s plus 1 over s plus 1 square plus 2 square minus 5 times L inverse 1 over s plus 1 square plus 2 square. But you see, for the second term you will need 2 on the top, because the Laplace transform of sine 2t is 2 divided by. So I will 2 divided by s square plus a square. So I will replace 1 by 2 and divide it by 2. Then you can read off the inverse transform of this. This is just the Laplace transform of cos 2t but shifted by minus 1. So the inverse transform is e to the minus t cos 2t. And this is 5 by 2 inverse transform of e to the minus t sine 2t. That's going to be the solution to your IVP. So let me end here, because the next thing, which is shift formula 2, will take this lecture beyond the limit of our usual class. So maybe I'll do that. So far we haven't seen, you see, when I started this, I said Laplace transform is going to be used, particularly when you have a non-homogeneous system with discontinuous right hand side. And that is what is still, we haven't done that yet. And it's when you have discontinuous right hand side, that's where shift formula 2 will come into play. But that's for the next lecture. So let me end it here. So this is a shorter lecture. It's probably ran only for 50 minutes. So ciao for now, and next lecture next time. That probably will be our last lecture. All right then.